Hi, my name's Dave Lannom with Monroe Training, and welcome to today's segment on circuit construction. Let's start with our agenda. First, we'll talk about why circuit construction. We'll do a quick review of series circuits as well as parallel circuits, and all the concepts that we're going to be covering today will be done as a demonstration. So, after we're through with that, we'll do a quick summary. So, why are we here? I mean, think about it. If you test a circuit as part of the diagnostic process, it is just as important to know what the readings should be as it is to know what the readings and measurements actually are. I mean, picture this. You have a 110 outlet in your house. You put the meter in the outlet and it says 90 volts. At that point, you know you're 20 volts shy. But if you didn't know that it was 110 when you started, was 90 volts good or bad? So as we develop skills in analyzing a circuit, its operation, it's easier to identify the circuit's fault. The faster the fault's identified, the faster the diagnosis is confidently completed. And I can't say it enough times. Confidence diagnosis leads to guess confidence, and that results in the referral of more friends, more family, and more coworkers. So when we look at circuit construction, we're going to talk about both series and parallel circuits. Now, if we looked at two different schematics, one of them on the left for daytime running lamps, one on the right for cooling fan motors, at half the operational time, they're running in series. The other half of the time, they're running in parallel. So as we run in series, we can see on the left, there's a split in the voltage. So the bulbs are very dim, but as we run them in parallel, we look to the right, we see, now they're operating normally. So the same circuit could be operated in a series at one time and a parallel in another. So let's talk about series circuits first. And first, what do that, we need to define what in the world is a series circuit. And by definition, a series circuit is a circuit that has only one path for current to flow. And here's what I mean by that. We take a look at this circuit that's wired in series. We start at battery positive power. We run power to the switch. From the switch, we run up to the first load. Then what we do is we run power through the first load to the second load, and then we use a single ground back to the battery. So when we talk about series circuits, there's a few rules that come into play. So let's talk about the rules. And the first rule is that total resistance in a series circuit is equal to the sum of the individual resistance, making it greater than any one of the individual resistances. Let me show you what I mean by that. As you can see, when we measure the first resistance, you can see what its measurement is. Then we measure the second resistance. And then when we measure the total circuit resistance, that is the value of the first resistor plus the second resistor, the sum or the total of the individual resistances was exactly the total circuit resistance. So, what's the second rule that we've got to deal with? The second rule we have to deal with in series circuits is voltage. And in a series circuit, the voltage in a series circuit is equal to the total of the individual voltage drops. Let me show you what I mean by that. I mean, if we take a look at the series circuit while it's operational, that total voltage is 12.62 volts. So once we've got that measurement made, at that particular point, what are we going to do? We're going to measure the voltage across the first load, and that's going to be what? Just about half of it, or 6.15 volts. We continue, we measure the voltage across the second, and once again, we've got 6 volts. The sum of those, the 6 plus the 6, equals the 12 volts that we started with. Now, this is the type of circuit that you see at daytime running lamps, where the lamps are running about half the brightness, or in the cooling fan circuit that we looked at earlier, where half the time it was running in low position, where it split the voltage, 6 volts and 6 volts in the low position. So from there, there's some rules about current. And the current in a series circuit is going to be the same no matter where I measure it. Here's what I mean by that. I mean, if we take this particular series circuit, here's what we're going to do. We're going to open up the circuit. We've got our amp meter. our digital voltmeter already placed on the amp scale, just like we did when we covered this in basic TVO amps. We know we're measuring current because the meter became basically a jumper wire. And at that point, we were looking at approximately 0.220 amps. Now, let's take a look at another place. Let's say this time, though, we're going to measure the current coming through the switch. And we know the meter is working as soon as everything lit up. And guess what? The same 2.2, 0.22 amps shows up that we had. So in a series circuit, no matter where I measure it, the current's going to be the same throughout the circuit. And remember this about series circuit. If one component fails, the entire circuit fails, just like cheap Christmas lights. Here's what I mean. Remember when we disconnected that first load? What happened? When we disconnected that first load, that particular point, neither one of the loads continued to function. So how else could we build a circuit? We could build a circuit in parallel, which is what most of the circuits that you're going to be dealing with in automobiles are today. So the first thing we'd have to do is define a parallel circuit. And by definition, a parallel circuit is nothing more than a circuit with more than one path for current to flow. Let's take a look at how that's constructed. We take that same circuit board and we have battery positive power. We run the battery positive power the same way through the switch. In this case, we run it up the load, and from the load, we ground that first load, causing that one to light. Now we go back to battery negative. Now let's go to the second one. We see a splice at the first load that's now traveling over to load number two. And again, load number two has its own ground or its own path back to battery negative. So that's how the circuit was constructed. Let's talk about the rules. And in a parallel circuit, the voltage is the same in each branch. So they share the same common voltage. So if I were to take a look at this particular circuit and I were to measure the voltage coming in at the source, I'd see that I had 12.24 volts at the source. We measure across the first load, and once again, we've got that same voltage, that 12.2 volts. We move over to the second load, and once again, the voltage is the same in each branch of that 12.2 volts. So let's talk about the rules for resistance when it comes to parallel circuit. And in this particular case, total resistance in a parallel circuit is always going to be less than any of the individual branches. I mean, remember the basic Ohm's law that the more current we had, the lower the resistance had to be. So if we provide another path for current to flow, then the total circuit resistance has to become less than that of the smallest one. And here, let me show you what I mean by that. As you can see, there's resistance across first load, and it's about 6 ohms. Once again, we measure the resistance across the second load. Once again, we're looking at 6 ohms. So now let's measure the total circuit resistance. Hmm, It's half of that because total circuit resistance was always less than that of the smallest branch. When we talk about current, the current in the circuit is going to be the sum of the individual branches added up. And here's what I mean by that. So let's say we measured the current, first of all, across the first branch. So we measured the current across the first branch, and we're looking at about 0.323 amps. So what do we do next? Let's measure the current across the second branch. And we measure the current across the second branch. Once again, we get about 0.322 amps. So what we said was the total current is the sum of the individual branches. So let's do this. Let's measure the total circuit current, and we'll do that by just running right across the switch. And when we measured that, it's about 6.4 amps. So the total current was in fact the sum of the total of the individual branches currents. Now remember those series circuit rules when we said if one component failed, the others continued to operate? Well, in a parallel circuit, it's a little bit different. If one component fails, the remaining components continue to operate. And that's really the way we need the car to operate. I mean, picture this. Can you imagine a world where if one of your light bulbs went out, that your horn didn't work, or if your wipers quit working, the radiator cooling fans didn't work? It's just not a practical way to build a car. So when we look at cars, we're pretty much looking at a circuit just like this one, where as soon as we opened up the first branch, the remaining branches continue to function. So now, let's do a quick summary. Remember, when you're testing circuits as part of the diagnostic process, it's just as important to understand what should the readings be, as well as what the measurements are. The series circuit rules were simple. If one component fails, the whole circuit fails. The voltage was distributed based on the resistance. And in a parallel circuit, if one component failed, the balance of the circuit continued to work. And there was source voltage across every branch. Hope this section on circuit construction has been helpful for you. Thank you and have a great day.